What's up, guys? I hope everyone is all right. Now, last time we talked about measure of dispersion, which is basically standard deviation. Now, today we are going to talk about normal distribution, which is something that we observe in our daily life over and over again, even if we don't realize it. Okay, so that's very, very important phenomena in statistics. Okay, let's see what it is. Here is the outline. So first of all, let's look at the motivation, or what is the logic behind it, or why we need it. Then let's formally define it, and we will look at Z-scores, and we will look at some applications of the normal distribution. So let's start. So here we have some questions. Actually, we are asking these questions. So when we go to a movie theater, most of the time we know that we don't feel that much uncomfortable with the seat. Okay, so we don't say it's too narrow or too wide. Okay, most of the time it fits us very well. But how can that be possible? Okay, but at the same time we know that for some people it may not be that much comfortable. Okay, so question is, how do manufacturers design or design those seats so that we feel comfortable with it? Okay. Another question. So it's about designing a car. So most of the time when we get in the car, we don't bump our head on its roof, right? So, but how can that be possible? So how do car manufacturers design those cars so that we don't have that problem? But again, we know few people are suffering from that problem. We know that. Okay, and another example, how long a tie must be so that it's neither too short nor too long for most men. Okay, so how do we answer those questions, or how did people answer those questions? Well, so we gather relevant data, and then so we use a curve, what we call normal curve or normal distribution. Okay, so that's the logic behind it, and today we are gonna see it. Okay. All right. So what are the properties of normal distribution? So it has a very well-known shape, what we call bell-shaped curve. It's like this. Okay, so it's like a bell here. So, guys, this is a curve, and we are not gonna go through the details, but here, in fact, this is probability density function. Okay, so you will see this topic in the future, but this is a probability density function. So these are probabilities. Okay, so these are probabilities, but let's just ignore it and just focus on the applications. Okay. So our curve, this normal curve, is symmetric with respect to the mean. Okay, so the mu here is mean, and sigma is the standard deviation. So just a quick note, guys. Whenever we assume that we are using the entire population, then mu and sigma will be used for mean and standard deviation respectively. Okay, that's very common convention. All right. So the curve is symmetric with respect to the mean. See, mean, sorry, what? Mean is at the center. Okay. So, and the area under this curve is 1. So guys, we interpret this one as 100%. So that means all of the data, or the entire data, lies under this curve. Okay, we interpret it like that. So from that perspective, roughly 68% of the data lies within one standard deviation. So what that means is, if you look at one standard deviation above and below the mean, okay, we have 68% here. Okay, we have 68% of the data here. You can say, in other words, this area here, guys, it's 0.68. Okay, and if you go for two standard deviation, that means if you look at from this point to this point, we cover 95% of the data. And actually it makes sense, right? Just look at this area. Okay, look at this area. We have a tiny area remaining here, tiny area remaining here, but rest of them, the huge amount of area is here. Okay, cool. Now let's see an example. Say we have 1000 students and we have their scores, and assume that the scores are normally distributed. Okay, it means that it obeys a normal distribution, and most of the time it obeys normal distribution. Okay, and say the mean is 450 and standard deviation is 25. Okay, so here's the question: how many scores do we expect to fall between 425 and 475? Now, 425 is one standard deviation below the mean, which is 450, and 475 is one standard deviation above the mean. Okay, so that means this interval, guys, this interval is nothing but one standard deviation below and above the mean. So if you go back to the previous slide, we know that 68% of the data should be there. Okay, so that's why we have 1000 students, 68% of them will fall within that region. Okay, will fall within that region. So second one, how many scores do we expect to fall above 500? Okay, what do you think? So 500, guys, we can say it's two standard deviations. Standard deviation is 25, the mean is 450, so 500 is two standard deviation above the mean. So what we know is, we know 95% of the data, or in this case the number of students, must fall within two standard deviation. Okay, so here we have two standard deviation. Okay, so these are two standard deviation. We have 95% of the data should be here, and remaining 5%, guys, should be below this point and above this point. Okay, 5% should be here and here. Since the shape is symmetric, we have 2.5% below two standard deviation, and we have 2.5% above two standard deviation. Okay, so let's go back to our question. So that means, in other words, 95% of the data must fall within two standard deviation. That means it should be between 400 and 500 in terms of grade. Okay, so 5% of the scores must lie more than two standard deviation. What that means is 5% should be above 500 and below 400. Okay, and since the shape is symmetric, we are gonna share them, right? So 2.5% will be below 400, 2.5% will be above 500. Okay, so the answer should be, because of that, answer should be 1000 students times 2.5%, 25. Okay, so the answer should be 25. Okay, now let's talk about Z-scores. So here's the definition. Sometimes we just call it just score. Okay, so it says how many standard deviations we are away from the mean. Okay, so when we are given a Z-score, it will directly tell us how much we are away from the mean, how much standard deviation we are away from the mean. So absolute value of the Z-score, guys, is gonna tell us how much standard deviation we are away from the mean. So the Z-score can be positive or negative. Most of the time we will look at the positive case because our shape is symmetric. So, for example, if your Z-score is 0, how do you interpret that? Well, we are 0 standard deviation away from the mean. That means we are on the mean. Okay, so Z-score 0 or 0 Z-score always corresponds to mean. All right. For example, if Z-score is 1, then that means we are 1 standard deviation above the mean, and similar interpretation for 2. Okay. So for example, in the previous example, 475 was 1 standard deviation above the mean. That means Z-score for 475 is 1. Okay, and similarly Z-score for 500 is gonna be 2. Okay, cool. Now, it can be negative, guys, as I told you before, but because of the symmetry of the distribution, we always use positive case in practical applications. So that's the first thing. Another point is it can be any number, all right? It can be any number like 1.23 or 2.05, but the idea is always same, okay? For example, if the z-score is 1.23, that means we are above 1.23 standard deviation. We are 1.3, 1.23 above the standard, above the mean, okay? And similarly, if the z-score is 2, let's say 2.05, that means we are 2.05 standard deviation above the mean, okay? So, but how do we find it? Okay, so how do we find all these values when we are given a z-score or when we are given any kind of raw score? How do we compute z-score? Okay, so we have a special table called ZTable. Okay, and in ZTable, guys, the mean, it's a convention. Mean is 0, standard deviation is 1. Okay, and we call this type of distributions a standard normal distribution. It's a normal distribution, but it's standard. Okay, whenever we have standard normal distribution, even if we don't explicitly say that, the mean is gonna be 0 and sigma is gonna be 1. Okay, now here's the z-table. So the first important point about z-table is this small shape, guys, okay, because there is no agreed upon shape about it. Sometimes some people use both sides of the curve, okay, left and right. Sometimes we use just one side, one area here, okay, one area. So in our book, in our textbook, this is the convention, okay. So these are the areas measured from 0, okay. These are the areas measured from 0. So let's go back to here. So how do we interpret? For example, let's take 1.1 here. So guys, here we have when we look at here, for example, first of all, let's look at this number, what that means. So these scores are here, okay. Actually, the numbers are here. Let's say numbers are here, and these are these scores, okay. So first of all, what is this number? What is this row and column? This one is 1.30. Okay, so this one is 1.3. For example, this one is 1.50, 1.54. Okay, so this point corresponds to, this is the z-score for 1.54. Okay, and this one, for example, is the z-score for 2.18. Okay, so we have ones, how do we call it? So the ones and tenths are gonna be here, okay. So the ones and tenths are gonna be here, and hundredths are gonna be in the row, okay. In the column we have ones and tenths. In the row we have hundredths, okay. For example, what is this? So this one is the z-score for 0.2, 0.52 or 0.52. For example, this one is the z-score for 0.91. Okay, and what is that actually? For example, let's look at this one. So this is the z-score for 1.3. Okay, this is the z-score for 1.3. So z is here. So that means the area from 0 to 1.3 is 0.4032. Okay, this is how we interpret that. That's very important. For example, for this one, this point, so z-score here 0.4382. And what is that number? 1.54. Okay, so that means the area from 0 to 1.54 is 0.4382. Okay, this is how we interpret Z-score. All right. For example, so using that table, Z-table, let's find the percent of the data or area under the curve that lies in the following regions for a standard normal distribution. Okay. For example, if you have 0 and 1.3, okay, 0, 1.3, what is that number? What is that Z-score? So we are gonna look at the area from 0 to 1.3. Okay, 0 to 1.3. Now let's go to the table. We are gonna find 1.3, which is here, and ta-ta. Okay, it should be 0.4032. Okay, so the area from 0 to 1.3 is gonna be 0.4032. What that means is almost 40%, almost 40% of the data lies between 0 and 1.3. Okay, this is how we interpret that. Right? So again, one more time, we use the leftmost column to find the ones and tens place, and the top row for the hundreds place. Okay, from the table again, guys, that number from 0 to 1.3, we found 1.3, that area should be 0.40 or 40%. So that means we expect 40% of the data to fall between 0 and 1.3. So how about this section? What is the area from 1.54 to 2.13? How do you find it? Well, so idea is the following. What are those numbers? I forgot it. 1.5 for 2.13. So first of all, I will find the area from 0 to 2.18. Okay, area from 0 to 2.18, something like this. And then I will find the area from 0 to 1.54, and that section is gonna be here. Okay, and I will look at their difference. All right. So area from 0 to 2.18, how do we find it? So we first go to the table. Okay, the area from 0 to 2.18 should be 0.1 is here, and then I'll go here. This is 0.18, so that corresponds to 48, almost 0.48. Okay. So to find that region, I will look at the area from 0 to 2.18 and subtract from 0 to 1.48. So we found it. So similarly, area from 0 to 1.54 is gonna be 0.43. So the difference is gonna be 0.04. So that means almost 4% of the data falls that region. Okay, that's very narrow region. What was the last one? Okay, so this is interesting. Between 0 and minus 1.54. Now guys, so 0 and minus 1.54. So how do we find it? So we will use the symmetry of the curve. Okay, so area from 0 to minus 1.54 will be equal the area from 0 to plus 1.54. Okay, and that area is from the graph again. Actually, we found it here, right? Area from 0 to 1.54, that should be 0.43. Okay, so that means almost 43% of the data will be in this region. Okay, now, so how do we convert a row score? Row score means just any score, we are given any distribution, guys. So see, in this table, in ZTable, we have a convention, right? The mean is 0, standard deviation is 1. But when we are given a data set, it will be probably different, right? We have a different mean, different standard deviation. But we have a very nice way to convert to ZTable. So let's say we have a normal distribution with the mean mu and standard deviation sigma. Then we use x minus mu divided by sigma to convert that distribution to that non-standard distribution to a normal distribution. Okay, because we want to use the table, and we don't of course we can make a table for that particular data set, but it's very annoying, right? So we cannot do it for all data sets. So we have a standard table. Okay, we have a standard normal distribution table. So whenever we have normal distribution, we are going to take it and convert to a standard normal distribution using this formula. So, for example, let's say a set grade roughly follows a normal distribution in the US population. So, and let's restrict the range to 200 and 800. Okay. So the average math score in SAT is 500 with a standard deviation 50. Okay, so find the corresponding z-score for the given grades. Okay, so the average is 500, standard deviation is 50, and we assume a normal distribution. And let's find the z-scores for these scores. Okay, for these grades and interpret it. Okay. So here's the formula. So this is the given score. Okay, 589. So this is our mean, and this is our standard deviation. So if you find the result, it should be 1.78. But how do you interpret that? So that means, first of all, guys, that means that score 189 is 1.78 standard deviation above the mean. That's the first interpretation. And when we go to the table, guys, 1.78, 1.7 is here, and then 8 is here. I lost it. 0.78 corresponds to this z-score, which is 0.46. Okay, so that corresponds to here. Okay, so that corresponds to 0.46 from that table. Now we know that half of the area, the left half of the area, is gonna be 0.5. Okay, 0.5, and the area from 0 to 1.78 is 0.46. Okay, so that means, guys, this person's score is better than almost 96% of the entire students. Okay, because he is already above the left 0.5. Okay, and he is also above the right 0.4. If we sum them up, we are gonna find 0.96. Okay, so that means this is pretty good score. Okay, on the other hand, let's look at other one, which is 397. So for z-score for that guy is gonna be minus 2.08. Okay, so from that table, using the symmetry, this value corresponds to 0.48, but please keep in mind this is minus. So in this case, 50% is on the right. Okay, 50% is on the right, this person is on the left. 50% is on the right, and from 0, the area from 0 to minus 2.06 is 48%. Okay, 48%. So what that means is this person's scores lies in the last 1.9% among the participants. Okay, so that's how we interpret that. All right. So guys, whenever you feel comfortable, please feel free to stop the video and just work on the problems by yourself. Okay, because that's very, very important. Okay, now let's look at two interesting applications. Okay, and these are very basic applications, but if you look around, guys, you will see there are thousands of applications of normal distributions in our life. Okay, now here's the problem. A machine fills bags of candy, and as we can expect, there are some irregularities in the operation of the machine. So what that means is it doesn't give exactly whatever it's supposed to give. Okay, so that means not every bag gets exactly the same number of pieces. All right, so let's say they assume that the number of pieces per bag has a mean 200 and standard deviation is 2. Okay, since standard deviation is 2, guys, we know that sometimes it's gonna put less than 200, the machine is gonna put less than 200, sometimes more than 200. Okay, but how do we quantify it? Okay, that's the question. For example, what is the chance, or scientifically, what is the probability that the machine is gonna put, for example, 209 candies in that bag? Okay, for example, let's look at this case. How many of the bags do we expect to have between 198 and 200 pieces in them? Okay, so that's a very practical question. And the second one is, how many of the bags do we expect to have at least 196 pieces? Okay, let's see. What we are gonna do is, guys, so first of all, look at that. The mean is 200, standard deviation is 2. So this is not a normal, this is not a standard normal distribution. This is normal distribution, but not standard. So we need to convert to a standard normal distribution. So how do we do that? We have two sorry about that. So we have two numbers here. We are going to convert them to a z-score. Let's do that. For 200, z-score is going to be 0, and we know that should be 0, right? Because if we are on the mean, z-score is always 0. For 202, z-score is going to be 1. Now, what was the question? Between 198 and 200. Now the question is, so what is the percentage of the data which falls between 0 and 1 in ZTable? Okay, and if you go back to the table, to ZTable, and we can find the area between 0 and 1 from that table is gonna be 0.34. So this is the z-score for 1, okay, and this is the z-score for 0, and their difference is 0.34. So we always interpret this score as percentage, right? So what that means is, so we expect 34% of the package to have between 198 and 202 pieces. Okay, so that's, sorry, this should be 200, right? There's a small mistake here. So we said pieces of them. Oh, this should be like this, right? We are making a mistake. So this should be 200, and there should be 202. Okay, so there is a small mistake here. Now let's continue. Okay, so between 200 and 200 pieces. Okay, now so then this should be we should fix it, right? So between 200 and 202 pieces. Okay, let's look at the other one. How many how many of the bags do we expect to have at least, this phrase is important, at least 196 pieces? Okay, what do you think? That should be a small amount or large amount? What do you think? So I feel like that should be small, right? Because see, this is standard deviation is 2 and 196 is 2 standard deviation below the mean. Okay, below the mean, so it's very far away from the mean, so it should be a small amount. But let's see, let's convert it. So 196 minus 200 divided by 2, this is how we convert to a z-score, right? So that corresponds to minus 2. Now this value again from the symmetry corresponds to 0.48. Okay, and again from the symmetry the area on the right of minus 2 is gonna be, so this is the right piece, this is the area from 0 to minus 2, 0.47. So if we sum them up, it's gonna be 0.97. Okay, so since we are looking at least 196 pieces, the result must be 1 minus that number, which is 2%. Okay, almost 2%. So that means the chances or the probability that the machine puts 196 pieces in the bag, in a bag, is very low. Okay, it's very small, almost 2%. Okay, another question. Now assume that the distribution of 21-year-old woman's heart rate at rest has a mean of 68 beats per minute with a standard deviation of 4 beats per minute. Okay, now we have 200 women or 200 women of the same age, of course, and we are going to examine them. So the question is, how many would we expect to have a heart rate less than 71? Okay, less than 71. So what do you think? It is something very small or very large? So without doing anything, guys, just looking at the normal curve, we can somehow interpret that. Let's try it. So mean is 68. Okay, mean is 68, and the deviation, standard deviation, is 4. Okay, so it seems, see, we are, so if you look at 71, it is more than 1 standard deviation above the mean. Okay, because 64, actually no, it's less than 1 standard deviation above the mean. Okay, it's less than 1 standard deviation above the mean, because 1 standard deviation above 68 should be 72, right? So this is less than that. Let's see. Okay, so x is, again, x is row score here, it's 71. The mean is 68 and standard deviation is 4. Let's compute the z-score. If we compute the z-score, it's gonna be 0.71. Okay, 0.71, and this corresponds to an area of 0.27 from the table. Okay, 0.27 from the table, and we know, we always keep in mind, guys, one more time. So we measure z-score from 0. Okay, from 0. So this left area, okay, this left area that we exclude is 0.5. All right. So because of that, oops, sorry, because of that, so this score for 0.75, so this score for 0.75 is actually this is the z-score, but this z-score corresponds to 0.2827, which is the percentage. So 0.5, it's already on the left, and we also have 0.2% here, and if we sum them up, we are gonna get 77%. All right, 77%. So what that means is we expect that the 77% of the women to have a heart rate less than 71. Okay, so this is the percentage. How many women did we examine? It's 200. So the answer should be 200 times 77%, which is 144. Okay, so that means 144 women should fall into that region. All right, guys. So this is the end of this section, and have a nice day, guys. I hope uh, everything is gonna be alright for you in the life. Take care, guys.